In the previous lecture, we learned about flow rates and defined a simple mass conservation per unit time expression for open systems, where mass is coming in and out of our system. Starting with the energy conservation equation, or the first law of thermodynamics for a closed system, if we differentiate with respect to time, we'd get that the change of energy over time, dE dt, is equal to q dot minus w dot. This means that in a transient system, the energy can be increasing or decreasing over time. If we now account for mass flow in an open system with one inlet and one exit, we'd have the same expression, only now we have energy associated with the amount of mass entering, mi dot times E, where E is the specific energy, and energy associated with the amount of mass exiting. This lowercase e would be all types of energy of that mass entering. Internal energy, kinetic energy, potential energy, etc. Sometimes potential energy is negligible, but if the inlet and outlet are positioned in a way where the difference in height is big, we would definitely take potential energy into account. And it's the same with kinetic energy. If we have a control volume around a nozzle, for example, we'd have much lower velocities coming in than those coming out, and we would therefore include the kinetic energy term inside our E variable. In general, before neglecting any terms, this equation would look like the change of energy over time, dE dt, equal to q dot minus w dot plus mi dot times ui plus vi squared over 2 plus gzi minus the same terms with the E subscript. This w dot term would of course be associated with shaft work or boundary work, for example a piston, which we call the system work, and it also includes the work needed to push that mass flow into the system or to take the mass flow out of the system. And that type of work is what we call flow work. Mathematically, if delta W is F dx, like we've seen before several times, and therefore delta W delta T is equal to F dx dt, we call what's on the left the flow work, W dot sub flow, and on the right we identified that the force is the pressure times the area, and that dx dt is the velocity. And if we know from the previous 8-minute lecture where we defined flow rates, link below, that the mass flow rate is density times velocity times area, or velocity times area over specific volume, then area times velocity can be written as m dot times specific volume. This means that flow work is pressure times n dot times specific volume. When mentioning flow work for the first time just seconds ago, I said the work needed to push that mass flow into the system. This means that whenever fluid enters our control volume, work is done to the system. And because of our convention for work done to the system being negative, this flow work would be negative for the inlet of the fluid. And with the same thought process, when a fluid leaves our control volume, its flow work would be positive. Going back to our main equation and substituting the flow work with these, we can write q dot as q dot system, because that's all the heat transfer we have, and we can split the w dot term into the w dot system, shaft, paddles, boundary work, etc., plus these two terms associated with the mass flow. Distributing the negative sign, we now see a much more detailed version of the conservation of energy equation for our control volume of an open system. Notice that at the end, after distributing the negative sign, mi dot pivi is positive, and mi dot peve is negative. And finally, when we factor out the m dot in and m dot exit in this expression, we can see that since enthalpy is the internal energy plus PV, we can substitute the U plus PV terms with the enthalpy H. And this is how we obtain the conservation of energy equation for our control volume of an open system with one outlet and one inlet. Now, if we have more than one inlet or more than one outlet, or both, the derivation doesn't change. We would just add more terms here if there's more inlets, and yes, with the positive sign here. And if there's more outlets, we would add more terms here, with the negative sign. These parentheses are sometimes grouped together as the variable theta. In that case, we would have a theta sub I and a theta sub E. In its most generalized form, this would be the conservation of energy equation for an open system. At steady state, remembering the definition we used during the last lecture, dE dt would be 0, since the energy would not be changing over time. If the kinetic energy and potential energy are ignored, we would have the sum terms with enthalpy only, H instead of theta. And if we only have one inlet and one exit, then we can get rid of the summations. Let's look at a simple example where we make use of what we've learned today, and as usual, don't forget to check out the links in the description of this video if you want to see more complex examples on this topic or the links to other thermal lectures. Air enters a 31 centimeter diameter pipe at 22 degrees Celsius and 180 kilopascals with a velocity of 5 meters per second. The air is heated as it flows through the pipe and exits at 160 kilopascals and 37 degrees Celsius. What is the average velocity and volumetric flow rate at the exit, and what is the rate of heat transfer to the air? Assume this system is at steady state. As always, pause here and try to solve this problem on your own before watching the solution here. In the previous lecture, we introduced the concept of mass conservation. We know that in a steady state system like this, the mass flow rate coming in must be the same as the mass flow rate leaving our control volume. And in this lecture, we introduced the concept of energy conservation for open systems like this. So we'll use both of these tools to find what we're looking for. If the mass flow rate is the same at the inlet and at the outlet, and we know that the mass flow rate is the velocity times the area over the specific volume, we see that because the pipe's cross-section is not being narrowed or expanded along its axis, the area in and the area exit are the same. Therefore, the average exit velocity is the average inlet velocity times the ratio of specific volumes VE over VI. From our ideal gas equation, the specific volumes are RT over P. After substituting these expressions, we can substitute the temperatures in Kelvin and the pressures to find the velocity at the exit. As also established in our previous lecture, the volumetric flow rate is the velocity times the area. We substitute the velocity and we calculate the cross-section area of a circle of diameter 0.31 meters. This yields the volumetric flow rate we were looking for. Now for the heat transfer, we can use the expression we developed today. Since we have a steady state control volume, the change in energy is zero. We're using the equation without the summations since we only have one inlet and one outlet. And since there is no gain or loss in height, meaning no gain or loss in potential energy, we can cross out those two terms. And finally, since there is no work at a system level, no piston, paddle wheel, shaft, displacing component, etc., W system is zero. With this, we see that the heat transfer we're looking for is equal to the mass flow rate times the change in enthalpy plus the change in the velocity terms. The mass flow rate can easily be calculated because we already have the volumetric flow rate for the exit, and we can quickly calculate the specific volume at the exit. And this value is the same for the outlet and the inlet, like we stated earlier. And by looking up a table for the ideal gas properties of air, we can find the specific enthalpy of air at 295 Kelvin and the specific enthalpy at 310 Kelvin. That is the specific enthalpy at the entrance and at the exit respectively. Now notice something very important here. When we substitute all values, we make sure that the units are consistent. This specifically means that if we just substitute the specific enthalpy values we get from the table, which are in kilojoules per kilogram, we cannot combine that with the kinetic energy components in meters squared over seconds squared. Kilojoules is equal to kilonewtons times meter, which is equal to 1000 Newton meter, which is equal to 1000 kilograms meters over second squared times m, which divided by kilograms results in 1000 meters squared over second squared. This means that we either need to write the enthalpies in joules per kilogram to be compatible with and the same order of magnitude as meters squared over second squared, or we keep kilojoules per kilogram and divide the kinetic energy terms by 1000, so that their units also become kilojoules per kilogram. Either way, we end up with a rate of heat transfer to the air that is equal to 14.51 kilojoules per second. Now, what would have happened if we didn't take into account the change in kinetic energy due to the change in the inlet and exit speeds? Well, if we don't take those terms into account, the result is now 14.50 kilojoules per second, a 0.07% error. So this is very important to remember. Neglecting the kinetic energy is not always the case because the inlet speed can be several orders of magnitude higher or lower than the exit speed. But whenever you have small changes in velocity, like the one we had here today, They are not going to contribute much because those differences are roughly 3 orders of magnitude smaller than the changes in enthalpy. This means that for small velocity changes like this one today, we could have just neglected the kinetic energy changes and written the rate of heat transfer as mass flow rate times the change in specific enthalpy. Like I said before, if you're interested in seeing other more complex examples using what we learned here in this lecture, or watching other lectures of the thermo course or even other engineering courses, make sure to check out the links that I've left in the description of this video. Thanks for watching.